In this video, I'll talk about the synthesis and some of the common reactions that the amide function groups go. Now, remember that amides are the least reactive carboxylic acid derivatives. So, as a result, you can make amides from acid halides, anhydrides, and even the esters. And the way of forming the amides from those guys is more or less very similar because they all kind of possesses a leaving group in there. And if I want to make a primary amide, I would use an ammonia. But if I want to make a secondary and tertiary amides, you can also do that. You just have to be a little bit selective with the selection of the amine that you're using in the beginning. So if you're using a primary amine, you would end up making a secondary amide and so on. So for example, suppose I'm trying to make, I'm just gonna go ahead and pick a different amide here, not necessarily in a primary amide, but I'm trying to make, let's say, in a secondary amide here. So if I'm making in a secondary amide here, I want to use CH3 NH2 here, excess. And if you don't want to use an excess, then you can just use CH3 NH2 one equivalent with pyridine. The whole point of using the excess or the pyridine is to just remove the proton at the end of the day. So your nucleophile here, which is the nitrogen, what it's going to do is going to go ahead and do the attack here. This is going to come out to make an a tetrahedral intermediate. But when this reforms, this leaves the Cl leaving group there. And that would still leave this nitrogen within a positive charge because I don't have that proton lost yet. So that's why you use a second equivalent of amine or even the pyridine to remove that proton. But at the end of the day, this is what you're going to be making in a secondary amide. And that's going to be the case for, I would say, the anhydrides as well. And even for the esters, you may not necessarily have to use a excess and amine. That's because the OCH3 minus that you're going to lose from that ester, they can also be act as a base, and that would remove that protonated nitrogen's proton on it, makes the amide. Now, in either case, it's a very similar scenario. I would have this nitrogen lone pair in case of an anhydride doing the nucleophilic attack in here, and then this breaks out. So I can just go ahead and draw an arrow here. I'm not going to show the mechanism, but just this is how it looks like. And when this reforms the pi bond or the carbonyl, this whole thing is going to leave. That's exactly what's happening with this guy right there. This whole thing is going to leave once it reforms the pi bond. This attacks here, this comes out. But when this reforms, this OR minus is going to leave, and that OR minus would be used to deprotonate that nitrogen at the end of the day. Now, when it comes to the acid, it's a little bit different because if you're just using the CH3 NH2 or an amine or an ammonia, it would remove this proton because remember that's an like acid as well. So then makes it a carboxylate. So that's not going to happen. So whenever you're using a carboxylic acid and trying to convert the carboxylic acid to an amide, you have to use a coupling reagent with it. So typically, a typical coupling reagent, let me see. The most common one is going to be the DCC in there. So you use the DCC coupling reagents very likely in the first step, and then you want to use the amine in the second step, and that would ended up making the amide. The whole point of using the coupling reagent is first to go ahead and kill off this acid here, or the proton here, and also make this OH in a better leaving group. And that would be an even better leaving group than what you have in case of an ester. I wouldn't really quantify or compare that particular leaving group with the chloride or the anhydrides, but it's going to be certainly better than the OH and the OR that you get in the esters. So remember that to form the amides from the carboxylic acids, and a coupling reagent is typically used. A most common one is in a DCC, but remember, this is really not the only coupling reagents. There are so many out there. And in sophomore organic, you would be seeing the DCC being written in there as the coupling reagent. When it comes down to the reactions of amides, amides don't really do a lot of reactions, and they do run hydrolysis. So if I'm doing the hydrolysis under basic conditions, the hydrolysis of any of the derivatives goes back to the acids, obviously. So I will end up making a carboxylate because remember this is being done under basic conditions. And then your second product here would be a CH3 and H2. Remember, I have this guy right there coming from this guy right there. So that's still an organic product. If I was running this under acidic conditions, how would that change? That would still be in hydrolysis, running under acidic condition. I would have a carboxylic acid made, and as far as that mean, it would be protonated now, so it would be an NH3 plus. So that's the acid-base reaction you got to be careful with. If I'm using an LiLH4 that's a strong reducing agent, the strong reducing agent will reduce the amides to an amine. So in this case, and a secondary amine. So it just basically at the end of the day kills off the carbonyl bond and makes it an amine. In this particular case, it would be in a secondary amine because we're starting out with a secondary amide here. There's one more reactions that the amides can technically do, especially if it's in a primary amide. So since this is in a secondary amide, using SOCl2 is not going to help. This works only with the primary amides. But if this was something like, let's say, in a primary amide, and go ahead and use SOCl2 here, that would turn this into an anitrile. That's in a very important reaction. Sometimes you see how you make an anitrile from an amide. Now remember, this only works if it's in a primary amide. If it's in a secondary amide, it doesn't really, the SOCl2 doesn't really convert that secondary or tertiary amide to an anitrile, only the primary amide. So these are the most common reactions that the amides will undergo.